Welcome to the Machines and Molecules podcast. Machines and Molecules hosts guests which have backgrounds in machine learning, biochemistry, chemistry, and life science. And our guest today is Aapo Hyvärinen, who many of you know probably from his very first contributions to the field. He's very famous for being the author of Fast ICA. He also worked a lot on noise contrastive estimation, think generative adversarial networks, for example, but also causal inference and many, many other very interesting contributions. I think he's a fan of academic traveling. He's been, apart from Finland, he's also been at the Gatsby unit at UCL, also in Paris, I think, and you have many collaborations all over the world. So, hello, Aapo.
Hello.
How are you doing today?
Oh, I'm fine, thank you, and thank you very much for inviting me to this podcast. So it's my very first podcast, so we'll see how it goes.
Yes, but as an experienced speaker, I think it would be no problem to you. So you've contributed to many different areas, and you have a very broad research agenda. Is there a certain pattern to how you pick topics?
Yes, there is actually a kind of a pattern. So many people say that I have a broad agenda, but in fact, like 90% of my work is based on basically one single mathematical theory, which is the theory of what one might call non-Gaussian latent variable modeling. So basically what used to be called independent component analysis. So that's kind of what I did my PhD on. And then I just kind of, based on that mathematical theory, I applied that theory to different topics, such as causal inference, modeling of the visual system, but it was still always the same mathematical theory. And then more recently, then I also, as a kind of a spin-offs, I had things like score matching and noise contrastive estimation. But in fact, even the idea of score matching came from this theory of ICA, where people have previously solved some certain sub-problems with that. But then this recent book, this is something rather different.
Yeah. So non-Gaussianity. So basically Gaussian distributions, they behave very nicely. They interact very nicely with linear models. Why is it important to go to non-Gaussian distributions? What does that change?
Well, first of all, yes, it is in some mathematical sense, a Gaussian distribution is nice. It's simple to understand and manipulate. You can manipulate the equations and so on. But at the same time, it's in a certain way seriously degenerate. It actually, certain problems such as identifying latent variables are possible for basically any other distribution than the Gaussian distribution. So there's a funny thing that the Gaussian distribution is simple, but at the same time seriously problematic in other ways. So that's one thing that, with non-Gaussian distributions, you can actually identify things that cannot be identified with Gaussian distributions. And of course, on the other hand, it's just reality. If you look at real distributions, especially in machine learning, signal processing kind of stuff, they are usually not Gaussian. And if you just treat them as Gaussian, you are certainly losing a lot of information.
And for our listeners from chemistry, biochemistry, what are latent variables and why would you want to look at them?
Well, latent variables, that is actually a deep question. Nobody ever posed it to me like that. It reminds me of there was a kind of an internet joke somewhere where there was a young man was on a psychiatrist couch, and the psychiatrist was asking, so these latent variables, are they with us here in this room? So that's the thing. The latent variables are kind of an abstraction, kind of something hypothetical which you use to explain your data. They may not be identical. In some cases, they actually correspond. Kind of the hope is that even though they are kind of hypothetical in the mathematical model, they would actually then correspond to certain real underlying processes that generate the data, which may be something that, that are actually real in the sense that you could measure them if you had some further measurement modalities, perhaps, or there might be something that describes certain like kind of a more abstract, some separate phenomena underlying the data on some more abstract level.
Mm-hmm. So for people maybe who came into life sciences, biochemistry from a medical background, factor analysis probably is close, right?
Exactly. Well, factor analysis is probably the oldest.
Mm-hmm.
Yes, I'm sure it is the oldest method for latent variable analysis.
Mm-hmm.
Yes.
And maybe for people from chemistry, if they were able in some way to do latent variable analysis, maybe as another explanation, there might be latent variables that explain the stability of a molecule or how soluble it is in water or other solvents. So this is basically one way to characterize data in a sense that you can take apart the different effects of different parts of the data, right? Is that fair to say?
I suppose so. I don't understand chemistry enough, but I can tell you kind of actually possibly the first example or application of latent variable models was by Spearman in 1904 when he pretty much invented factor analysis. And his idea was to find intelligence. So he had a lot of like measurements about certain subjects. I think they were probably school children actually. And then he wanted to find this kind of a general factor of intelligence, as he said. And that is what he did with factor analysis.
Mm-hmm. Yes. And our theme here in Machines and Molecules is that the guest brings a third word. Have you brought a third M word?
Well, in fact, I have a kind of a super bonus M word, which is mindfulness meditation.
Why is that?
Well, it's because my newest book is really kind of it's not, I cannot say that it's about mindfulness meditation. It's largely about related phenomena. And kind of in the end, if you actually read the book until the end, in the very last chapters, then it is shown how mindfulness meditation relates to all this and how, it's kind of a culmination in the book is to show the connection to mindfulness meditation. And it has two M's.
And why? So what is it about in the beginning if it's not about mindfulness meditation?
In the beginning, it starts with human suffering. So shall I explain the synopsis of the book now?
Yes, please, go ahead.
Okay, so, the book starts with human suffering. So what is human suffering? Where does it come from? How can it be possibly alleviated? And it uses a theory of AI for this, because AI is basically, AI has always been like half neuroscience. Especially for me, when I started doing AI, actually, I kind of wanted to do neuroscience, but I had a background in mathematics. So how do you combine? How do you do that? How do you do neuroscience when the only thing you actually know is mathematics? Well, AI is one answer. So now this book starts by looking at this one particular theory of AI, which is a theory of intelligent agents, which means like kind of it could be robots or it could be software-based agents that are actually like acting in the world. That's why they are called agents. So they're acting in a world, which means that any action that they take changes the world a little bit. And then what they need to do is to find actually the best sequences of actions to reach their goals.
Yes.
And so the reason why this is relevant is that when I started looking for kind of a clear definition of suffering, well, I looked at old philosophers, basically the Buddha and other Buddhist philosophers, and also Stoic philosophers in ancient Greece and Rome, especially Epictetus, which is, I think, kind of basically the most underrated philosopher in Western philosophy. And when you look at what they talk about suffering all the time, well, everybody knows that Buddhism is very much about suffering, but so is Stoicism. And what they talk about is the idea that it is actually desire and the frustration of desire that is really the basis of suffering. And this is the basic starting point for the theory in my book. And now if you think about intelligent agents, robots or whatever, they actually, they decide that I will try to reach a certain goal. Maybe I will try to clean this room or whatever. And then they take actions to reach that goal. And they may fail. because there are various problems in the world. And when they fail, this is actually defined as suffering. So when the agent does not get to the goal where it was trying to get.
And so this is super interesting. I heard about this book from Matthias Bethke, and I was like, wow, okay, so somebody else made the connection as well. Did you start out being interested in suffering really, and then you looked up the literature, or were you, for example, doing mindfulness meditation for a longer time, and then it just came to you that there's a connection?
Yeah, maybe like the latter. So I've been doing meditation for a long time, and also reading Buddhist philosophy and Stoic philosophy and so on. Maybe in the very beginning, what I wanted to do is to write some kind of a theory of what happens when people meditate. But that's actually extremely difficult. One reason why it's difficult is that it's that let's say modern neuroscience is not really about, it doesn't know very much about the phenomena involved in mindfulness meditation, because mindfulness meditation is about, something that happens, what one might call intrinsic dynamics, things that just happen inside your head, so that you are not actually like doing anything with your limbs, and you are not receiving any sensory stimulation. And this kind of intrinsic activity is extremely little understood in Western neuroscience, which is really focusing on like sensory processing and motor control. So, but then, I started thinking about these things, and I realized that these ideas that are more like formulated on the level of philosophy, these ideas that I just described, what is suffering? And suffering is actually not getting what one wants, something like, and from that, making then the link to like neuroscientific terminology like frustration and so on. Well, that kind of then actually I think, opened the way to actually approach these ideas. Not so much, it's a bit difficult to approach meditation, but it's a way to approach Buddhist philosophy and related ideas.
I'm not completely through the book yet. I started to read it last week on a flight. What struck me was that maybe you're not too big a fan of the ideas of now is the only time that matters.
That's a complicated question. I mean, of course, there's always, when you write this kind of a book, there's always the question that what do you want to write about, and what can you actually write about? Like I just described, in a sense, I wanted to write a book about mindfulness meditation, but then it just didn't work out like that way, because it's very difficult to say much about that. And what I can talk about is the idea of suffering and these more like philosophical ideas about where it comes from. So again, like if you say that now is the only time that matters, well, I might actually, kind of agree with that idea on a personal level, but what to say about it from a scientific viewpoint, that's another issue, and I might not actually be able to actually write anything scientific about it.
Yeah, understood.
And in fact, it's in some sense, it is a little bit implicit in the book, which is very much talking about predictions. It's emphasizing the idea that suffering is usually related to predictions. Like the basic case of frustration. So I predict that, okay, I will do certain things and then I will get what I want, but then actually I don't get it.
Yeah.
So if there were no prediction or no expectation that I will get something, then there could be no frustration either.
Yeah, that's true. This idea, maybe to people who are not into mindfulness, this idea of now is the only time that matters, and related to what you just said about predictions, I think it was Mark Twain who said, I've known a great many troubles in my life, most of which never happened, right? So that's the whole idea. Like you think about everything that could go wrong, or how you could do this and that in the best possible way. But then really very little of this matters in the actual real world. And this is one of the ideas in Buddhist philosophy. And this is something that you also talk about right now by saying, okay, you make these predictions and then these things don't happen in exactly that way. And you inflicted a lot of suffering on yourself by, well, my prediction was wrong, but do you really suffer any disadvantages from it, real manifesting disadvantages?
Yes, and there's I think two things. One is predicting, so people's brains are predicting all the time what will happen. But then there is the idea of simulation. There is actually one chapter on simulation, and especially in the form of wandering thoughts. So when you try to focus on something, it often happens that you actually start thinking about something else. And even if you don't, especially if you don't try to focus on something, then suddenly you will start thinking about all kinds of stuff that might happen to you. And here exactly we get to this idea by Mark Twain that we are simulating in our brains things that might happen to us, and that brings us a lot of suffering. We also recall things that happen to us, especially unpleasant things that happen to us, and that again creates a lot of suffering. And this is exactly kind of a completely kind of, well, almost useless suffering. Even though, well, in that chapter in the book, I also talk about computational theories about why this is actually useful from a computational viewpoint. Because the thing is that when you think about future, what might happen to you, it's a form of planning, and planning is a computationally extremely expensive operation. So it's a good idea to do it, if you don't have anything else to do. And there's also sophisticated theories in reinforcement learning, one branch of machine learning, about why it would actually be useful to repeat unpleasant things that happened to you in the past. Why it's useful thing to repeat them in your mind, because it actually helps you to learn about them. On an intuitive level, it's obvious you can learn from them, but there's actually an exact mathematical theory of why that would happen. It's a question of what people call experience replay.
Yes, that was something. That was an idea that I recognized in the book that I had before as well when reading Eckhart Tolle books, where he talks about, well, don't care about the past, don't care about the future. Now is the only time that matters, and many things resonated with me, which is maybe odd to some of my friends who know me as a very scientific person. But also I was like, yeah, but wait a minute, there is a use to recalling old things. But as you say, you recall only mostly the bad things, and probably
Yes.
the use of this is, well, you learn from only the bad things. The good things you don't need to learn from so much.
Yeah, and the bad things they are the most important ones, especially, well, there's no point in recalling episodes in the past which were completely neutral, because there's nothing important in them. So then you could choose either bad things or good things. And it's a little bit of a mystery, in fact, why we tend to recall the bad things more than the good things. In fact, the theory of AI, this theory of experiential play at the moment, seems to say that we should equally well recall the bad things or the good things, but then it's actually an established fact in psychology and neuroscience that people tend to recall the bad things. And it is maybe a little bit of theory still missing, that why is it that people mainly recall the bad things?
I mean, this is only speculation, but might it be that we have a conservative drive because AI agents, they might die. Humans don't care about this so much because we can just spin out another AI agent. If it's software only, it doesn't cost anything at all. If it's hardware.
Yes, I think that is perfectly possible. That might be the explanation. Yes. So yeah, robots don't really care about dying. They don't have a survival instinct, at least for the moment.
Yeah.
Yes.
True. And you said the book didn't turn out quite as you thought because there's lacking theory. Was there other things that you learned while writing the book?
Oh, well, actually, I learned a huge amount of things while writing the book. Actually, if you want to learn about something, one of the best ways is to write a book about it. I mean, of course, this is kind of something that we do to some extent. We write notes, and at school or university, we are forced to write, essays on various kinds of stuff. And well, the ultimate thing is then to write actually a whole book about some topic. But I really spent a lot of time like searching for related literature and reading it and then putting it all together. I mean, it was a long process that took me basically 5 years. So yeah, I really learned a lot. Yes.
Yeah. And you put it online for free, right?
Exactly. Yes.
and it's called Painful Intelligence, and you can find it on the archive.
Yes, and there's a homepage, even a web domain,
Really?
painfulintelligence.info.
Okay, that's very nice. And when have you pushed it online?
It was June last year.
June last year. Okay,
Yeah.
very nice. Um, so yeah, maybe let's shift gears. Maybe tell me a bit about what you think you gained from visiting many different institutions like Gatsby Unit in Paris. I'm not sure where in Paris you have been based.
In Paris, I was at in Indria-Saclay, so in the new University of Paris-Saclay on that campus. Well, I mean, actually studied it much earlier. When I was an undergraduate student, I started my studies at the University of Helsinki. Then I went to University of Vienna, where I was for like 3 semesters. And then I went to Paris. I studied in Paris for 3 years. So I really liked traveling already as a student. Then I went back to Finland and kind of, in some sense, settled in University of Helsinki. But then again, I wanted to travel a little bit, and I went to Gatsby and Paris. So what do you learn? Well, of course, one thing you learn is foreign languages. Especially when I was studying in Paris, I mean, everything was in French, absolutely everything. Also in Vienna, everything was in German. But these days, of course, it's very different. You go to another European country and you study in English all the time. Well, at least you know you learn English with the various local
That's
variants.
for sure, yes.
But otherwise, well, I suppose you get some kind of a general culture also about universities. You see how there are well, people. I suppose people talk about these things like tacit knowledge in a kind of in the work of experts, so something that cannot really be like expressed very well in any written form. And so you see how people work, what are their kind of working styles, motivations, and so on and so on, and which are then maybe rather different in different universities. Possibly also they may differ from one country to another, but maybe more importantly, they just differ from like one university or department to another. There's this kind of a microcultures here and there. And so, yeah, maybe this I think this sounds very vague, but I suppose, well, you certainly learn something about how people do science.
Yes, I think so very much. Even just going from Germany, where I did my undergrad and PhD, to France, it looks like a tiny difference, but from the tiny difference, you can learn so much. I think really even the approach to excellent science is quite different in France. They kind of celebrate it even, and they have a very hard system, I have to say,
Yes.
for students. It has changed, by the way, in Paris. People start to talk much more English in the last 8 years, basically, I think.
It's completely different. I mean, when I was studying in Paris, I mean, the idea that you would actually do university studies in English in Paris, it was just a complete logical contradiction. It's not that it was impossible in practice. It's just kind of a completely pointless idea. I mean, senseless idea. But yeah, these days you can do it very easily, actually.
Yeah, that's true. I actually, at the airport, I gave the lady my passport, and I started talking to her in French, but she insisted on talking in English to me. So it was really odd. Yeah. So yes, I think the first time I've really touched base with your work was when I saw a talk by Michael Gutmann. Was he your PhD student, or?
He was my postdoc.
Your postdoc, okay.
Yeah.
So he was talking about noise contrastive estimation, I think at a Monte Carlo conference. And to me, it just blew my mind in that moment that you can do these very sophisticated, highly rigorous statistical things with it. And back at the time, I think even guns were not a big thing. So what is it about noise contrastive estimation that makes it work so well? And maybe you can explain it to people who haven't looked at it yet.
Yes. So the basic idea is actually very simple and intuitive. I mean, the way we started it is that, well, we just thought about, okay, just from an intuitive perspective. So let's assume that the basic goal is that we want to find interesting features in some data. For example, very high dimensional visual image data. It could also be some very high dimensional scientific measurements. So we thought that, okay, if you actually train like a neural network to classify to perform a classification where you have two classes. One class is the real data, and the other class is just some complete noise, so just like maybe Gaussian noise. So in order to make this be able to classify these two, discriminate between these two classes, presumably the neural network has to learn something deep about the structure of the data. And so, okay, we had actually we did just completely heuristically, empirically in one paper that's now completely forgotten. But then a little bit later, then we understood that actually it's not just a heuristic idea. It has a very rigorous mathematical basis, which is that in fact, the neural network can be seen as estimating the probability density of your data. Basically, the idea is that, well, any probabilistic classifier will learn the ratio of the probability densities in the two classes. Now you know the probability density in the noise class because you created it yourself. So then if you know the ratio and you know the probability density of the noise, then you can calculate the probability density of the data. And that's, of course, one of the deepest problems in all machine learning or statistics, how to estimate the probability density of your data.
For example, what is the probability distribution of natural images? And then you have to understand what are people, what are dogs, what are, I don't know, glasses, and all of these different things that are reflected in just loads and loads of pictures of the real world, right?
Yes, and this is how these modern like generative AI tools work, image generation. So the typical image generation methods these days, they have one part that is estimating exactly this probability density of natural image data. Maybe in a more sophisticated way, maybe it's actually looking at the gradient of that, and maybe on different scales and different levels of additive noise and so on and so on. But essentially, the goal is to estimate the probability density of the data. Once you have that, then you can do so many things. For example, you can generate new data points from this distribution, and that's how you generate the new images.
So what you're referring to when you estimate the gradient, this is not the GANs, this is diffusion models, right?
Exactly. Yes.
Yeah.
Yes.
Yeah.
Oh, actually, it's the part of the diffusion models. They don't estimate exactly the probability density, but they are by anything like noise contrastive estimation. They estimate the gradient of the log density using score matching.
So basically, they estimate how you go from. So what you referred to earlier, it's basically they estimate how you can go from complete noise closer and closer to something that looks more and more like the data points that you have in your data set, right?
Yeah. So this is actually all rather complicated and confusing. And now, especially when we are talking about noise, it's actually not noise in the same way as in noise contrastive estimation. So these diffusion models, they are actually very complicated. They're using very sophisticated mathematics like stochastic differential equations and so stochastic processes, so as to optimize the way that you generate data from the probability density that you have more or less estimated. Also, there's the problems that people tend to use methods which don't exactly estimate the correct probability density, but some kind of a convoluted versions of that. And so it's all very complicated. But in principle, the basic principle is that they have like one model for the probability density function, and then they have some kind of an MCMC model method for sampling from that, and that's it.
Yes. And to go back to noise contrastive estimation, probably one of the beauties of this is that you can use this artificial task to classify the actual data from something that you create in order to fit your model in a very smart way. So you can turn something that is unsupervised learning into a supervised learning task, right?
Exactly, yeah. So that's what people call now self-supervised learning.
Mm.
So I think at the time we published NC noise contrastive estimation, I don't think anybody had ever used the term self-supervised learning. But now this is exactly one of the kind of a basic methods for self-supervised learning. And now these days it's something that is extremely popular. And well, generally speaking, it is this idea that if you only have like a data set without any labels and you want to do something like understand something about the structure of that data, well, you kind of generate kind of a completely artificial, completely like in a sense completely meaningless classification task. And then by solving that classification task, like I said before, the neural network has to learn something meaningful about the structure of the data.
Yeah.
And yeah, these days people have developed like dozens, maybe hundreds of different tasks that that basically force the neural network to learn something about the data. So I think possibly our paper was the first one to propose a classification task with exactly this purpose.
What excites you at the moment about the field? Maybe in areas that you're not explicitly working on yourself?
Well, that's a difficult question. Of course, what excites me most is my new book. Oh, well, in areas that I don't know. Well, I suppose, well, this answer is a bit banal, but I might say something like ChatGPT. It has, of course, like it's completely amazing and has kind of, yeah, nobody quite understand how, well, a few years ago, nobody would have predicted that kind of stuff is possible at all.
And will ChatGPT come and kill us all?
It will not probably in itself. Actually, I talk a little bit about those ideas in my new book. So yeah, there is this idea, well, human beings and any biological being, well, organisms have some kind of a survival instinct. But then the question is whether computers or robots might actually acquire that instinct. Well, to put it shortly, I discussed that in the book, and some people say it's impossible. Others say it's perfectly possible. It's actually, I think, an interesting topic for future research. People at this moment have some vague ideas and have mainly perhaps a little bit like emotionally charged ideas. Some people say, okay, it's really dangerous. Some people say, no, it's not at all. But it's actually a place where we could do serious research and look at various conditions under which robots could do something unpleasant because they may develop something a little bit similar to a survival instinct.
Yeah, that's a good question. I mean, if they develop a survival instinct, does that mean necessarily even that they do something unpleasant? Because survival maybe doesn't depend on us being dead, right? Or
that's one point. Yes, and well, the first thing we should actually do is to have, well, what I would like to see is like a clear, formal mathematical definition of what it means to have a survival instinct. What's the very definition? And once we have that, then we can start discussing what are the conditions under which it could actually develop in robots, and how then in that case then we can understand how we could prevent it and so on. So one thing that actually that I find a bit funny is that people tend to associate the idea of consciousness with survival instinct. I think, well, from a neuroscience perspective, or whatever, these have nothing to do with each other. Survival instinct is basically some kind of a behavioral tendency. It means that the agents, whether animals or robots, they tend to behave in certain ways that something about preventing them from dying or so on, while consciousness is something completely different. Consciousness is something that is actually extremely mysterious. Well, the biggest unsolved problem in the universe, presumably, about which we cannot say very much. The only thing we can say is that it doesn't seem to have a lot to do with the actual like contents of the information processing or your behavior. It's just something that comes perhaps at the top or something. Computers can do very intelligent things without any consciousness. Simple animals presumably don't have consciousness. Still, they can do complicated things. They can have a survival instinct. So consciousness, at least in my opinion, is something that's almost independent of the actual contents of what kind of information processing is being performed.
But also, there's no formal definition, I suppose. So.
Exactly. Yes. Yes. No formal definition, no even like operational definition. Neuroscientists have been thinking about how can you tell whether an animal is conscious, and nobody has. It's not clear at all. There are different opinions, but no consensus whatsoever.
We could go on and on about this, but it's already time to wrap up the podcast. Maybe as the last question, what advice would you give to someone who just gets started in machine learning?
Well, I think my standard advice is that you should learn more maths, unless you have actually already majored in maths or something. But people often come from a computer science background, and they just don't have really the mathematical prerequisites that you need to very successful research. So that would be my advice.
That was definitely true for me in my PhD. Yes. Super. Thank you very much, Aapo.
Thank you very much.
It was a pleasure having you, and I hope to see you at a conference soon.
It was a great pleasure for me. Thank you very much.
Bye-bye.
Bye.